All right, so we are going to hopefully finish up everything that we'll need for the test today. So this is all the end of the new material, and then as I said, Thursday we'll do the practice. But let's try some stuff we did last week. It's a little fuzzy. There we go. Is that better? Hold on. All right, it should be fine. So let's start. So find the perimeters and areas of the polygons and figures below. And I have a couple more. I don't know if we'll do them. We might be short on time today. I want to make sure we get through all the material. So let's just do this one and see how we are. All right. So it's the perimeters and the area. Remember, the perimeter is the length around some figure, and the area is how much space that figure takes up in like the 2D plane, right? So in this figure, I already broke it up into sections for you because you'll note that it's a composite figure. And composite here just means more complicated, I guess. More complicated slash, and it also means like, what's the word? A concatenation, like a bunch of more simple shapes glued together. More simple shapes glued together. Right, so that's all they mean by composite. Like basically this whole big shape, if I outline the outside here, like that whole big shape is the composite figure. And then what I already did for you is I broke it up into smaller shapes, all right? You also note that there's no units here. So our units in the end will just be nothing. I won't write the units. If you really want to write units when there's none given, you can put units. Like, so if it's perimeter, it'll just be units. If it's area, it'll be units squared, but that's your preference. Anyway, so let's do it. So I'll do each of these three sections on their own and then put them together at the end, right? Because remember, when we do composite figures like this, we find the area of each smaller, simpler shape and then add them up to get the area of the total figure. So, and you can label them, maybe I'll do that. So I'll say this is A1, A2, and A3. I'll do the areas first and I'll do the perimeters. So area A1. Okay, and so the A1 and A3 are both circles. I'm getting, sorry about that. All these spam calls. A1 and A3, as I said, are circles. Like I don't know anyone in Denver, Colorado that should be calling me. And so I've given you the radius here. The radius of A3 is 3, and the area, or the radius of A1 is 2. So recall and also they're half circles, right? At least we can consider them to be half circles. So it's half pi r squared. R is 2, so 2 squared. 2 squared is 4 times 1/2 is 2 pi. Again, no units. For A3, I'll do the A3 right now because it's another circle. So it's in the same, and it's another half circle at that. And, you know, technically, I'm telling you it's a half circle, but it might not have been clear from the shape whether it was or not. So if you're worried about that, just, you know, I'm telling you it's a half circle. So 1/2 pi r squared again. And the 1/2, again, comes from the fact that it's half a circle. So the area is exactly half of that of a circle. And then the radius in this case is 3. Right, and so I get 1/2 pi times 9, or 9/2 pi. However simplified you want to be. Questions about those? Alrighty. And A2 is probably the easier of the three areas. A2 is just you can think of it as a rectangle, or even more, it's a square, right? Because the sides are the same length. So the area is just side times side, or length times.
You wrote 3. You wrote A3.
Thank you. A2, not A3. That's what I get for numbering them in a different order. But yeah, so as I said, it's a square or rectangle, so it's just length times width, or side times side, so it's just 6 times 6, or 36. Right, and then to get the total area, you just add those all up. Right, so total area is, so it's 2 pi plus 9/2 pi plus 36. And strictly speaking, that is an exact answer. If you want a decimal though, you can always compute it. So 2 pi, again, if you don't have pi in your calculator, just use 3.14 or more digits if you like. I just use 3.14. And then plus 9/2 times pi plus 36. So I get, so it's about 56.4. And again, no units given, so I will leave them off, but it would be units squared. So that's my total area of this figure. All right, and then the perimeter is, I think the perimeter is a little less work. So I'll put that over in this corner here. So for the perimeter, remember the perimeter is the area or the length around it. So like if you took a string and wanted to put a string around this figure, how much string would you need essentially? That's the area or the perimeter. So what you do is just add up all the sides. So I have 6 here, I have 6 there. So this is the perimeter. So I have 6, I said, plus 6. And so that gives me this length and that length. And now the only question is, what is this half circle and this half circle in terms of a perimeter? And we know that the perimeter, we did this last class, right? The perimeter of a circle is called its circumference. So really what we want, and we want half the circumference of this circle and half the circumference of this circle, because these are both half circles, right? So the circumference of a circle with radius 3 and half the circumference of a circle of radius 2. So the circumference, recall, was what? Pi d, or 2 pi r. So it's going to be plus 1/2 2 pi times 2, and then plus 1/2 2 pi times 3. Right? So this is just 1/2 circumference. Right? And then you just add those up again. Right? And just like before, this was technically a sufficient answer. It's an exact answer. This is also an exact answer. But if you want a decimal approximation, we could plug in our calculator. So let's do that quick. So I get 6 plus 6 plus, let's see, so 1/2 times 2 is, so the 1/2 and the 2 cancel, right? And so I just get 2 pi. And then the 2 and the 1/2 cancel again in this bottom one, and so I just get 3 pi. So altogether, I get about 27.7. Apparently, I'm rounding to 1 digit today. All right, so my perimeter is about 27.17, sorry. 27.7, and my total area is about 56.4. Again, this would be units squared, and this would just be units, where units would be whatever the units of this is, the numbers are. All right, so that's a quick little memory jog. Any questions with that? Again, so with composite figures, we're just breaking these more complicated shapes into ones that we know how to compute the areas and perimeters of. I don't know how I'll do this. I don't know if I did one of these on the test. I can't remember. I think the last problem, and the last 3 problems I think on the practice test are geometry related. The last one involves a volume, and the other 2, the second last one involves a triangle. And so the first one about geometry I think involves areas, but I don't think it involves composite shapes. I don't remember though. We'll look at it Thursday. But you should, these are good practice anyway. All right, let's just do B, which is a lovely little ice cream cone. Right.
These added into the notes because I don't have those.
Yeah. So on the notes, I wanted to do a couple, but I didn't want to like waste a piece of paper by just putting a whole blank sheet. So I just added these. So this is, if you have just get a piece of scrap paper and put a couple of other examples on there, or if you fit them on the front page, that also works. But yeah. So this is like page one dash. And again, I think I'll just do B here. So it's a lovely ice cream cone. This side is 14. And we'll say it's symmetric. So this side, even though I didn't write it, we'll say it's also 14 inches. This time I have units. This dotted vertical line is 10 inches. And then across the top of the ice cream cone is 16 inches. So this length here is 16. Right? And this is a half circle right on top. So if this is 16, this length across, and again, we're assuming this is exactly a half circle, then necessarily, if I put the dotted line down the middle from here to here would be 8 inches. And so here to here is 8 inches, here to here is 8 inches. So basically this top part, you could think of as half circle of radius 8 inches. Right? And this bottom part you could think of as a triangle. Right? And so this bottom triangle as a whole is not a right triangle, right? This bottom chunk, ignoring the top circle, is not a right triangle. But if I chop it into two smaller triangles, I can make them two right triangles. So when you're doing this problem, you can do it one of two ways, right? The first way you can do it is you can consider this shape just to be one triangle in one half circle, or you can consider it to be two triangles in one half circle. Either way gets you the same answer. I'll just consider it to be one triangle and one half circle, but just note that either way is acceptable. All right, and so this is one triangle. And then you'll note that the base is 16 inches. And the height is this dotted line going down the middle. And height, 10 inches. Great. If you're doing two triangle way, you would have two triangles, both with base 8 inches and height 10 inches. In any case, we'll just use the formula 1/2 base times height. So the area, I guess I'll put it over here. And I'll put total area. Right. So the area of the circle we've done before, right? That's going to be 1/2. And then the area of a circle in general is pi r squared. So it's 1/2 pi r squared, where r is 8. Right? And so what is that? That's 8 squared is 64 times 1/2 is 32. So that's 32 pi. And then I guess I'll leave it exact until the end. And then my units are inches squared. Okay. And then my triangle, as I said, the area of that is 1/2 base times height. So that's 1/2 16 times 10. All right. And so the total area is just going to be 32. Oh, this is inches squared again. So it's going to be 32 inches squared times pi plus this 1/2 times 16 times 10. Right. And of course, we can get a nice decimal approximation. 32 pi plus, what is this? This is 8 times 10 is 80. So it's about 180.5. And again, inches squared. All right, so it's quite a large ice cream cone. All right. Any questions with the area? Again, we're just doing the two smaller shapes and using the formulas that we did last class to compute their areas, and then we just add them together because it's a composite shape. We're breaking it into smaller pieces. And then the perimeter, should do the perimeter as well. Perimeter in this one's just like the other one. All right, so for the perimeter again, we want the total length around. So again, think of it like you have a string and you're wrapping it around this figure and you want to see how long your string has to be to make it all the way around. So around one time. So I told you that this is 14 and that's 14. And don't check my numbers. I don't think this is probably, I just made these numbers up. So this might not be a real triangle. Like if you look at it, like this side's 14, this is 10, and this is 8. I don't think that's a real triangle. So it's a fictional triangle, but it will work for our purposes. If you wanted it to be perfect, you could have like taken, you know, you could have chosen this to be 10, this to be 14, and then use the Pythagorean theorem to find this third side. But this is, I just wanted nice numbers for an example. Anyway, so the perimeter is going to be 14 and then 14, right? And that gives you this like caret bit. So that's 14 plus 14. And then the only thing left is this top dome from the circle. And that is exactly half the circumference again. So it's 1/2 2 pi r. So 2 pi r here we said was 8, right? There you go. And the perimeter, as I said, is in length. It's the length of that string. So it's in just units, in this case, inches. And again, if we want a nice decimal approximation, we can do 20 or 14 plus 14 plus, and then the 2's cancel here as well. So it's just 8 pi, or pi times 8. And you'll see it's about 53.1 inches, just flat. All right. So it's a lovely, lovely ice cream cone or snow cone. It's more like a snow cone, which is unfortunate because snow cones are horrible. Have you ever had a snow cone that actually was delicious? Anyone?
I love snow cones.
You love snow cones? What about snow cones? Snow cones you love?
I don't know. I just really like chewing on ice.
Oh, okay. There it is. Whenever I've had them, like the delicious syrupy bits drip to the bottom of the cone, and that's it. The top is just ice. Well, I guess if you like ice, that's its own thing. But anyway, all right. I'm sorry if you like snow cones. I apologize. All right. Any questions about the example? We'll just do A and B here. I'll skip C. All right. So if you have any questions about composite figures, let me know. We can do more. We're not really in that much. We're not really in any rush, I guess. I mean, I think I'm like a week behind where I wanted to be as far as the timing goes, but it doesn't matter. There's not like a really strict schedule for this class. We're just kind of taking our time. All right. Anyway, volumes now. So this is the last topic in the geometry section. And volumes are super interesting, actually. If you take, I mean, if you at some point in your life end up going and taking more math classes and you take the calculus sequence, so Calc 1, 2, and 3, the third calculus course is all about three-dimensional things like this. And it's really interesting. Gary, your wife went to Pumpkinville and had cider slushies. Were they good, Gary? I don't know. Gary's gone.
Yeah,
were they?
Yeah. I mean, it was also my first time having or drinking through a paper straw as well. So that was an interesting experience.
They're kind of weird. I've only done that once as well. It's kind of bizarre. Yeah. But anyway, sorry. Sometimes I miss the chats when I don't. When I'm not looking at them. I appreciate the input though. Anyway, yeah, so if you end up going back and taking like a calc course, Calc 1, 2, and 3, the sequence in like some other college or something, you do a lot of really cool things with shapes, more than just what we're doing here. But a lot of the stuff we're talking about, you can actually go back and like prove and figure out where these formulas come from in a very concrete way. So it's actually beautiful. But we're just talking about the volumes and we'll do some examples with them. Nothing involving calculus. Anyway, so the face is a flat side of a three-dimensional figure. So like, well, we'll draw some examples and I'll show you what I mean. Polyhedrons are shapes that have 4 more faces, each being a polygon. So basically you take a bunch of polygons and imagine you're in 3 dimensions now. You've popped out of like flatland and you're in 3 dimensions and you have a bunch of these flat like pieces of paper, right? And they don't have to be rectangles. Like this is a rectangle. It's a flat. Pretend it's perfectly like rigid, so it's not flopping around. And suppose you have a bunch of these and you put them together with tape and make a new like object out of these flat polygons. It's a polyhedron. Assuming all the sides like meet nicely and there's no holes, no weird gaps. That's a polyhedron. So as an example, a cube is a polyhedron. And let me get a pencil so I don't screw this up. So we have a cube, right? And again, it's 3-dimensional. So this is like the front of the cube, and then you have the back of the cube, which I'll draw with dotted lines. Right, it's a cube. And so if you count the sides, right, you have 1, 2, 3 on the front face. And then on the back side, you know, where these dotted lines are, you have 1, 2, 3 as well. So a cube is a six-sided polyhedron. It's kind of a mouthful. So it's a six-sided polyhedron. And so each face is one of these rectangles. Or I guess it's a cube. So it's a square. So each face is one of these squares. Each face is a square. Right. Can you visualize that? So again, you just take 6 squares and you're in 3 dimensions. So pretend you're like a 3-dimensional, like omniscient being who can create faces out of their hands and put them together. And so you put these squares together in such a way that you create a thing. Gary, you raised your hand. What's up?
Yeah, I was just wondering. So if it's a polyhedron, so a polyhedron can be a cube.
Yeah. So
okay.
Polyhedron is just the umbrella term for anything with 4 or more faces, which are polygons. So all of these examples on this page are going to be polyhedrons. Yeah.
Oh, okay.
Yep.
Because you corrected yourself when you said rectangle or something, and then you said cube.
Oh, well, yeah. I was talking about this. I was kind of talking about the second case that we'll get to in a minute. But so if it's a cube, each side has to be a square because all of the lengths of the sides have to be exactly the same.
Exactly. Okay.
Yeah. So like if I were to label this diagram, this would be length S, this would be length S, and then the height would also be length S. So like for instance, like a 2 foot by 2 foot by 2 foot box is a cube. But like in this next example, rectangular prism, we can have something where the sides aren't the same length. So maybe like this. Right. So this would be a rectangular prism because this side has length L, this has length W, and suppose this has length H. So L, W, and H don't have to be the same, whereas in a square they do. So you could consider a cube to be a rectangular prism where all the sides are the same. It's the same way you can consider a square to be a rectangle where the sides are the same. It's just in 3 dimensions. And this rectangular prism, if you count the sides as well, or the faces, you'll see you also get 6, right? 1, 2, 3, and then 1, 2, 3 in the back side where the dotted lines are. So it's a 6-sided polyhedron. Each face is a rectangle. Right. So 2 examples of polyhedrons. And the next is also something you've seen before. A pyramid, right? So if you think about it, a pyramid, it also has flat sides, right? Because the only thing that we require is that each face, or you can say side, is a polygon. So it's like a flat 2-dimensional surface, essentially, on this 3-dimensional object. So if I drew a pyramid, oh, that's gonna be terrible. It's gonna be okay. I'll do this down. Wait, I gotta make it like symmetric. There we go. How about this? That's gonna be better. There you go. It's like a pyramid. Yeah. All right. I should have done it from a side. The only problem with doing volumes is the shapes are more difficult to draw. It's fine. All right. So I have. There you go. So I have a pyramid. And this is like you're looking right on the one side. So I guess I could draw another picture over here. Maybe it's like. I want you to be able to see both sides, but I don't know if I'll be able to get it. There you go. I don't know. That's not a very good picture. Basically, you picture a pyramid, right? I don't have like an object that's a pyramid, but you have 1, 2 sides. And then on the other side, of this pyramid, you have 1, 2 more, right? There's 4 sides. And then on the bottom, you have the base. So it's a 5-sided polyhedron. The 5-sided polyhedron. And then 4 of the faces, 4 faces are triangles. 1 face is a square. Okay. Can everyone visualize a pyramid? I don't know if you can have a base of a pyramid be a rectangle. If you're the base of a pyramid be a rectangle, I don't know what if that's considered a pyramid anymore. It's still a polyhedron, but all right. Any questions about these examples? Again, all of these are examples of polyhedrons because their faces are polygons, and there's 4 more. Cool. So let's look at some examples of shapes that don't have such nice straight edges, so that aren't polyhedrons. So I remember that a polygon is just something that has straight edges, that like, you know, so anything that's made out of like lines essentially in the plane is a polygon. So if we have something that's not made out of straight lines, then it won't fit this definition of polyhedron, although it will, you could still describe something that looks like that as a solid. So for instance, if I had a cylinder, and I'll say circular, so it looks something like this. So I have a circle, right? And then I'm going to extend it up. Imagine like a beaker in chemistry class. I don't know why I can't draw today. It looks something like that, right? And so the circles on the top and bottom are the same. They both have radius r. And the height I'll denote by h. Right? So again, just 2 circles, and you extend it up. Right? It's like a slinky. Imagine you have a slinky, right? And you have, you know, it all coils up. So you lift it, and if you basically like took that object that it constructed in space, that's a cylinder. It's a circular cylinder. Now you have to fill in the walls a bit, but it's still kind of a circular cylinder. We also have a cone, right? So a cone is sort of a cylinder, but in the case of the cone, the shape of these circles is changing. So what I mean is that you have something like this. All right, so at the base, it's some circle of radius r, and then it also has some height, of course. But when you get to the top, it peaks, and that's it. Right? So it's really interesting, actually. Like if you took this shape, right, and suppose you had this shape, and suppose it was an object that you could put in a deli slicer. And so you took this cone and you put it in a deli slicer, and you took slices of this object, like arbitrary, you took all infinitely, like all these slices, right, of the entire object. You'd get a bunch of circles, all of getting like radius getting bigger. So like you start at the tip, right, and it'll be a single point. And as you work your way down this cone, it gets like bigger and bigger, 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 bigger until you hit the base, and you end up with a circle of radius r. And so you can describe this object as basically an increasing radius circle that you kind of slice together. All right. And then lastly, a sphere. Right. And I'll just, I don't know, I'll leave it like that. It has some radius r. So we know these things. And again, none of these are polyhedrons, because so the sphere has no faces, right? The sphere is just round. So there's no flatness on it whatsoever. So face, the definition of a face makes 0 sense here. In this cone case, you could almost consider the base to be a face, and then the top like sheet to sort of be a face. You wouldn't define it that way because they're not polygons, but you could think of it that way. And the same with the cylinder. You could almost think of the top and the bottom as sort of the faces, and then the part on the edge to be sort of like a face. But again, we don't think of it that way, but you could. Right. So any questions about these? Again, they're not polyhedrons because they're not made up of polygons, but they're still solids, right? So we can still talk about their volumes, stuff like that. So moving on, let's actually compute these volumes. So my pen again. The volume of an object is just like the area is the amount of space a figure takes up in the plane. The volume is the amount of like space that an object takes up in the three-dimensional realm, right? So we kind of, everything has just been bumped up a dimension. So just to get an idea of what that means, let's look at an example. So suppose you have a box that is a cube. So it's 4 by 4 by 4 feet. In cubic feet, how big is this box? And how can you interpret this graphically, right? So the way we're gonna do this, and I'm sure most of you can compute the volume of a box already, but if you don't quite understand, let's look at this graphically. So I have this box, right? And it's 4 by 4 by 4. And I'm playing a dangerous game using my pen. Right, so it's 4 feet by 4 feet by 4 feet. All right. So now, suppose that you have a bunch of tiny little boxes that are all 1 by 1 by 1 feet. And you should know by now that nothing I draw is to scale. So don't even check. So you have a bunch of these boxes, right? And suppose you're putting them in the big box, all right? Imagine you work at FedEx or something, all right? So basically the volume of the big box in this example is going to be exactly the number of small boxes that you can fit into it. Does it make sense? So if my box is 4 by 4 by 4 feet, right? Then I can fit obviously 4 of these boxes tall, and I can fit 4 across, and I can fit 4 across that way. So if I'm looking like top down on this big box, right? So 4 feet by 4 feet. So this is a top down look on the big box. And so the question is, how many of these little boxes can I fit on the first level, right? So I put one here, and so I'm down to 3 feet. I put another here, and another there, right? So I can fit 4 across, and then I can fit 4 here as well. And I can fit, along like that, and then like that, and then like that, and then like that, and there, right? So, because each side is 1 by 1, right? So each of these takes up 1 by 1. So 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. They're all 1 by 1 by 1. So I can fit 4 by 4 by 4 by 4. And so in all, I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 boxes. 16 boxes on one layer, right? So on one layer of the big box, I could fit 16 smaller boxes. But I said I could fit 4 layers in because each of these small boxes is 1 foot tall. So I can fit 4 layers. So on each layer, I can fit 16 boxes, and I get 4 layers. So that means I can fit 4 times 16 boxes. And that's what, 64? So I can fit 64 small boxes.
Couldn't you just do 4 squared?
You could do 4 cubed, yes. But that's so fun.
That's what I meant, not squared.
Yeah, it's all good. But that's why you're doing the cube. Like if you know the volume of a box is just length times width times height, or in this case it's a cube, so it's side times side times side. The reason you're doing that is exactly this. You're basically packing 1 by 1 by 1 units, in this case feet, boxes into your big box to see how many of these small boxes can fit. And so the answer to this question is that it's 64 cubic feet. So it's 64 small boxes, or 64 cubic feet. Right? So this is the actual answer. but again, you can interpret it in terms of these small boxes, which are each 1 cubic feet. Yeah, down here I say, observe that the units for volume are cubic, because volume describes a 3-dimensional solid. So when we did areas, we were talking about squared things because we were talking about 2-dimensional objects, right? They had length and they had width. In 3 dimensions, we talk about objects which can be measured in 3 dimensions, so length, width, and height now, right? And so our units in volume terms will always be cubic, feet cubed, inches cubed, meters cubed, whatever. Questions there? All right. And so now, as was alluded to, we have nice formulas for all of these things. So in the case of a cube, like I demonstrated, it's just going to be side times side times side will be your volume. And I'll just draw a little diagram here. So side, side, side. So the volume, I'll leave it as V to be consistent, equals side cubed. Okay. Okay. And then units cubed. That's implicit. Right? So if it's a cube, you just cube the sides. If it's a prism, let me draw that again. So something like that. And again, you have length, width, and height, where since it's a rectangular prism, they're not all necessarily the same like they are with a cube. I have length, width, and height. In this case, as I said, my volume will just be length times width times height, all multiplied together. Right? For a pyramid, and honestly, I don't think I've ever computed the volume of a pyramid before. So it's kind of interesting. So I wrote it down here so I didn't forget it. I mean, it's not complicated, but it's odd. So for the pyramid, let's see it. So you have like a face like that. And so for the pyramid, basically the length and the width are the base of your pyramid. But the height is, so like with a triangle, the height is how high it goes. It's the same idea for a pyramid. The height is how high the pyramid is. So maybe I'll put that like off to the side. So this is height of pyramid. Right? And with those variables, your volume formula is length times width times height over 3. So again, I've never seen that one. I've never had to use it. So it's kind of interesting. Any questions with any of those 3? So these are the volumes of these first polyhedrons we did. But as I said, we can do even things that aren't polyhedrons, we can compute volumes of. So we can talk about the cylinder. And again, this will be a circular cylinder. So the circular just refers to what the base is. Strictly speaking, you can talk about cylinders that have any shaped base. And we'll get to an example at the end of class that has that. But the base of a cylinder doesn't necessarily have to be a circle. So that's why I referenced circle. But it just looks like this, as I pointed out. Again, your bottom is and top are both circles of radius r, and they have some height, h. And so the volume of a cylinder is going to be the volume of the base. So it's gonna, I'll write that in, volume, or the area, sorry, the area of the base times height. In this case, the base is a circle, right? So the area of the base is going to be, oops, no 2. It's going to be pi r squared, and then times h. And there you go. It's kind of exciting. Questions with that? And we'll do some examples, as I said, once we finish the rest of these. Just an FYI, so this cylinder, the way this formula comes from is it's back to the deli meat slicer, right? So like you take this cylinder and pretend you actually have it, like maybe it's a ham, or maybe a bologna is a better example. You took a bologna and you chop the ends off so it's nice and flat and circular, and you're feeding it into a deli slicer, and you get these slices that are circular, right? And so basically the area, what you're doing to compute the volume is you're just adding up the areas of all these slices. And that's all it is. So volume is just a sum of areas of deli slices of your object. And again, if you take calculus, you develop a language wherein you can talk about a deli slicer in a technical sense. It's not actually called a deli slicer, but that's really what you're doing when you to compute these volumes in particular. You're taking infinitely small deli slices of this object and you're adding up the areas together. And that gives you this formula, right? It's the same for the cone and the sphere, actually. They're a little more complicated deli slices, but you do the same thing. You just take deli slices of the object, you add all the area up, and that gives you the volume, right? So remember the cones just look like this, like a cone that I don't know what they use cones, traffic cone maybe? Looks like a traffic cone sort of, but the top comes to a point. It has some height. Oh, I'll do the height the same way I did the height up here. It has a height like this. It has some circular base, which has radius r. And so the volume is just pi r cubed over h over 3. And this formula, if you're thinking, this formula kind of looks like the pyramid formula, doesn't it? Right? It's kind of cool. So the pi r squared h is the volume of a cylinder with radius r and height h, and then you divide it by 3, and for some reason that gives you the volume of this cone. On the other hand, the volume of a pyramid is the volume of a rectangular prism divided by 3, and for some reason that gives you the volume of this pyramid. So if there is a relationship, and there's an underlying reason why these both are divided by 3, but it's not something we can get into. But it exists. I just wanted to let you know. All right, and then the last one is a sphere. And as I said, a sphere just is, it's a sphere. It's an object which has radius r. So again, for the sphere, the radius, if you rotate this radius around in 3 dimensions, so you can bring it out towards you can bring it back towards the sheet of paper, you can bring it down and up and around and all 360 degrees in every direction, it all has radius r. So the only thing you measure for a circle is the radius. And so that's what the volume is in terms of 4/3 pi r cubed. Right? Any questions about these formulas? Again, I'm sorry we can't really get into where they come from necessarily outside of the rectangular prism, but just know it involves like a deli slicer. All right, so let's try some examples. So determine the volume of a sphere with radius 6 feet. Write your answer in exact form and an approximate form, round to the nearest hundredth. Be sure to include correct units. This is a very wordy example, but let's try it. So again, it's volume of a sphere with radius 6 feet. So I go back and look at my things, my lists, and we know we just talked about that. Volume is 4/3 pi r cubed. So I go over here, volume, write it down, 4/3 pi r cubed. R is 6 feet, 4/3 pi times 6 cubed. And then oh, and I guess I should follow this through. So here's what I'm going to do. So it says, I've been kind of hinting at this, but it says write your answer in exact form and approximate form. So the exact form, as I mentioned, is when you leave pi in the answer, because pi, when we talked about initially, it never repeats, and it's this long infinite decimal. So I said you could use 3.14, but when you round, that's an approximation. So the approximate form is when you plug it in your calculator. So if I plug this expression in my calculator, so I get 4/3 pi and then times 6 cubed. I get 900, and it even gives me the digits to round to, hundredth, nearest hundredth. So that's what, 2 places? So 904.78, and it's feet cubed. Right, so that's my approximate form, because I plugged it in my calculator. My exact form, you can leave it like this, or if you want, you can multiply 4/3 times 6 cubed, and then just put a pi in front of that. Either, that works. So let's try that. So I'll do that. I'll do 4/3 times 6 cubed, and I get 288. So my answer can also be written as 288 pi feet cubed. That's the exact. Right? So again, the exact form is when you just leave the pi in. This also works for an exact form, but it looks nicer to compute what 6 cubed is and then divide it by 3 multiplied by 4. Right? But that's your discretion. Either of these I would consider exact. Right? And that's it. That's the volume of this circle. It's quite large. Circles get big as the radius get big. Right? Questions? Right, let's try another. So this one is an actual application. So what holds more oil? An oil drum with a radius of 2 feet and a height of 3 feet, or an oil drum with radius of 3 feet and a height of 2 feet, right? And so if you were asked just to guess, it's not really clear at all, right? Because 3 feet radius versus 3 feet high versus 2 feet radius and 3 feet high, like they're very similar. So you're not going to know without computing it. So what we have to do is we just have to compute the volume of each of these cylinders and see how much oil they hold, right? Whatever has the bigger volume will hold more oil, and that will be our answer. So let's do oil tank 1 and oil tank 2. We'll do like a little head-to-head. All right, so for oil tank 1, which I'll consider to be the first one given, I have a radius of 2 and then height of 3. In oil tank 2, I have a radius of 3, height of 2. And then these are cylinders. I don't tell you that. I guess I should have meant to be a little more precise. But I'm considering them to be cylinders. So we'll go and look at this formula for a
Well, if anybody's seen an oil drum, they know it's a cylinder.
Oh, is that true? Okay.
Yeah. But I mean, I don't.
I'll take your word for it. I don't know what oil drums
Yeah,
look
I
like.
live right next to all of the oil
Okay.
rigs, so yeah.
Good. So I guess it's not too off kilter. So it's a circular cylinder. And so you go to this and you realize the formula is pi r squared times h. So now we just need to compute that for both. So the volume pi r squared h. And so I plug in my variables. So I get pi times r is 2 times 3. And so what is that? That's 4 times 3, right? It's 24. Pi. And then everything's in feet, so it's feet cubed. And I can do the same thing for oil tank 2. So it's pi r squared again, h. Plug in r is 3, so it's pi times 3 squared times 2. And so what do I get here? I get 9 times 2 is 18. So that's the 18 pi feet squared. Surprisingly enough, oil tank 1 wins. Right? And you don't even need to plug these in your calculator. You could in this case, but you don't need to, right? Because you know that pi is the same in both. So if I'm comparing one to the other, oh wait, I'm sorry, this is 4 times 3. This is 12.
One of your variables has a 3 on it, and the other one has a 2 for the exponent. On oil tank 1, it says feet cubed.
I'm
on
sorry.
oil.
There we go.
Okay,
Thank you.
I was like, what the heck? It's happened a couple times
Sorry.
earlier too, and I'm like,
Oh, you should
is that a
correct
2
me.
or a 3?
Yeah, always yell at me. I'm sorry. I'm telling you, I make mistakes. All the units should be cubed. But yeah, sorry. So yeah, 4 times 3 is 12. This goes back to my 8 times 6 situation. It's 12. And then this one's 4 times 2. Or 9 times 2. Wow, I'm really off my kilter today. It's 9 times 2, which is 18. Pretty sure about that. Anyway, so oil tanker 2 is the winner. So that's the one that holds more oil. And yes, definitely cubic feet because we're doing volumes. So it's going to be a foot by a foot by a foot. So it's 3 feet multiplied together. So the units for that are cubic feet by definition. But yeah, questions with that one? right? So you can do examples like I think maybe on the practice I put something about trees. I think I said on the practice test. I think the last question is like you have two tree trunks, one of which has one radius and one height, and the other has some radius and some height. And I ask you to compute which tree will give you more firewood. And it's essentially the same question. Tree trunks are circular cylinders, give or take. So I'm asking you basically to do the same thing. So if you're trying the practice test, which you should, try to do the practice test before Thursday if you have time. That's how you're going to do it. Right, and let's just do a couple of regular volume ones, and we'll be good to go. How exciting. Right. So this one, find the volume of the following solids. Right. So this is just a pyramid. When you're doing these, make sure you can identify what the shape is, or what the figure is, or solid. That's obviously, if you can't figure out what the shape is, or what kind of shape it is, then you can't find the formula, so you're out of luck. And so you just go back and look at page 5 here, and you see, oh, we said the volume was length times width times height over 3. So we're going to use that formula. That's right. Length times width are just referring to the base dimensions. So the base of your pyramid is just like the flat floor that it rests on. So in this case, it's 5. I'll call that L, and I'll call this W. And note that the length and the width are arbitrary. Like it doesn't matter what you name which. It doesn't matter as long as they're the floor. And the height is literally how tall it is. And so here this pyramid is 8 inches tall, it looks like. So I get length 5 times 6, width times 8, height all over 3. And this is inches cubed. So let's see, what is that? That's 2, 10, 80 inches cubed, I think. Cool. So again, the formula for the pyramid and the cone are very similar for the same reason. So they're kind of interesting, and I do wish we could talk more about where they come from, but it's kind of outside the scope of this class. It gives more reason to take calculus one day. All right, this is a cylindrical cone. We've done a couple of these already. This one's just given to you. We're in meters, so that's our unit. So our final units will be meters cubed, but we call the volume of a cylindrical cone, circular cone, cylindrical, circular cylinder. There it is. Is pi r squared h. And the way you can remember this is basically you're taking the area of the base and just multiplying it times the height. Right? Because this is true for any cylinder. Right? So in our case, this is just going to be pi. R is 1 meter. And then h is 8. So it's just 8 pi. And again, it's meters cubed. That's your exact answer. And again, you can use your calculator to get a nice numerical answer. So what do I get? I get 25.1 meters cubed. Yeah. So either of those work. Right. Issues? Anything? All right, let's just do one more. This one's a cool one. It's so cool, I put a star next to it. Right. All right, so this is not a shape we've talked about, or I should say solid we've talked about. This is the base is a trapezoid, right? This bottom figure here is a trapezoid. So the base, this is a cylinder with trapezoidal base. Right. Again, we haven't talked about this, but I have mentioned that the volume of a cylinder is going to be the area of the base times the height. And remember, I don't know if I've talked about cylinders, but cylinders in general is you have some shape and you just stretch it up, right? Or down or whatever direction, sideways, left, it doesn't matter. So like if I don't have anything, like this is a circle, but pretend I have this eraser, right? So this eraser, think of it as just like this shape. And then imagine that shape and you stretch it along, like you stretch it out long ways. Like if this was made of like clay and you could stretch it without deforming that shape, that would form a cylinder that would be the shape of this eraser, but like long, like just a long form of this eraser, if that kind of makes sense. And you can do it with any shape. So in this case, I used a trapezoid and just stretched it up, right? And so I stretched it up 16 feet. The trapezoid has side, I think we called this B1 and B2 when we did trapezoids. So this was B2 is 16, B1 is 8, and the height is 5. So recall area of trapezoid. Remember that was, what was it, 1/2 H B1 plus B2. So that's the area. And so the volume is going to be, it's going to be area of base times height. So the height I said was 16. And the base, the area of the base was 1/2 H B1 plus B2. So I'll label this one B2. I'll call this one B1, and I'll call that H. So my formula now for my base area will give me 1/2 times 5 times parentheses 8 plus 16.
All right, I'm confused for a second.
Yeah.
That looks like a rectangle cube. I mean, I know it's not a cube, but a rectangular. Like, where do you see the cylinder part in it?
Oh, so it's not rectangular because it's not a rectangular prism, even though it kind of looks like one, because this bottom portion is not a rectangle, right? Because these two sides kind of go out. So,
Okay.
oh,
Okay,
I
but
see what you're seeing. Okay. I'm sorry. I can understand what you're saying. Like it kind of looks like the perspective is that this is just a rectangle. I get it. I can draw. Let me draw it like this, maybe. So like, what if I do? So what if I do like?
I understand where you're saying that it was coming from, like that. It's kind of like the top of a truck.
Yeah. It's just like the top of a truck. It looks like that. So like you have this part is a trapezoid, right? If you cut it off there, this bottom part is a trapezoid, or this side part, I guess. And the same, this side part over here is also a trapezoid. And you're
Okay,
kind
but
of,
I don't understand where you get the cylinder from. So I
oh,
don't see any
it's
circles.
it's just called a cylinder. That's just the name of it. Usually we think of cylinders like chemistry, like cylinders like circular, so they have a circular base and they kind of stretch up. But in general, you can talk about a cylinder as being anything that has some base that is then basically replicated infinitely many times, like stretched. So like this, you can think of as a cylinder, where this object is your base, and you basically just stretched it out. If the terminology cylinder is confusing, don't think of it like a cylinder. You could think maybe you could call it probably a trapezoidal prism. Trapezoidal prism, I think, also would work. So like maybe I'll put that. So cylinder with trapezoidal base, or trapezoidal prism. So I think that's acceptable. So like in the same way, the rectangular prism has all the sides are rectangle. I guess it maybe isn't strictly, but you can kind of think of it that way. Yeah, sorry about any confusion. But in general, for that idea, again, it's just area of the base times the height. So 1/2 H, I said in this case was 5. Let me just finish this, and then I'll draw another picture before class ends. 5, 16 plus 8, and then times the height, which is 16 as well, right? So in a calculator, we can just get an answer, and then I have another idea I can draw a picture of. 1/2 times 5 times 16 plus 8 times 16. Oops, eek. So 960. So it's 960 feet cubed. Right. Let me just draw one more picture, and then we'll call it a day. So, because again, this won't be on the test, but I just think it's really interesting. So 960 is that one. But let me just show you. So if I have some shape, right, it's like a squiggle. But what you can do is you can take this and you drag it up, and you have the same sort of shape. All the way up, and even on the back side, like it connects. And all the way around, you have that same shape. Right, and so like, it's just like, this would be called a cylinder as well. Anything where you have one shape and you just copy it to make that object is called a cylinder, and you truncate it at the end, you cut off the ends so they're flat. So this would be a cylinder with this as your base. And so if this object had height h, then this object will have volume h times the area of that base, whatever that is. So that's the definition of cylinder, that where I'm kind of coming from. For our purposes, you can, and for as far as the test goes and everything, you can just think of a cylinder as a circular one, like we talked about earlier, not necessarily in this more general sense, where you have weird things like trapezoidals and uglier things like that, right? So if you're confused, just think of it like the circle, like this, and what would be good enough for us. All right, any questions? Cool. So
I do have one question.
Yeah.
When we're taking the test, are these pictures going to be pre-drawn? 'Cause
Yeah.
I cannot draw to save my life.
You don't need to draw anything for the test.
Or is it
Basically,
kind of just putting in the equation, writing what number we're on, and calling it good enough?
yeah. So like on the practice, for instance, as I said, I have like an example, like, let me see if I can find it. I have an example like this oil drum one where you don't need to draw anything for it. You just need to know that you're talking about two circular cylinders is all. So you won't have to draw or anything for the test, so don't worry about that. Yeah. Any other questions? All right. So I'll see you Thursday. We will go over the practice. As I said, try to do the practice before then, or at least look at it and see what potential questions you might have. We'll go through the whole thing, but the more questions, the better. And yeah, hopefully the first test will go good. So I'll see you then. Let me know if you have questions about the homework too.
So test isn't Thursday, it's next Tuesday?
It's Tuesday. Yeah, it's the
Okay.
29th. Thursday will just be the practice. So I'll go over it in class. And kind of we'll review for the test essentially. Yep. Alrighty. Well, I'll see you
I
then.
have a question.
Yeah.
Okay.
Where can I find last week's Zoom?
It should be on my YouTube. It's on the link's on Blackboard.
Okay, perfect.
Yep.
Thank you.
No problem.